It's a popular T-shirt.
Well, I guess you are allowed for 3 minutes. You probably can do it on the other. Yeah.
Okay, welcome. Are there any questions from last time? I'd like to start with a comment that perhaps I should have said yesterday, but I'll try to emphasize again today. When we think about nearly ADS2 gravity, so we have an ADS2 space, a rigid ADS2 space, and then all the gravitational modes correspond to the motion of the boundary. So remember, the boundary was where we patched this nearly ADS2 geometry to perhaps some 4-dimensional geometry or to some other, some ADS or some other boundary configuration, right? So the motion of this particle within the rigid ADS has to do with the boundary gravitational mode. So the gravitational degrees of freedom are not propagating here in this setup. And this is the same reason why in spherically symmetric configurations in 4 dimensions we don't have gravity waves, so we don't have spherically symmetric gravity waves. But we do have non-trivial gravitational effects, and they are characterized by the motion of this boundary particle. And so when we think about dynamics of matter plus in this nearly ADS2 configurations, we have fields that propagate as if they were in ADS2, in a rigid ADS2 space. And the only coupling to the boundary is through an overall constraint that says that the overall SL2 charge should be 0. So there is an SL2. Remember the same SL2 we talked about yesterday for that acts on the boundary degree of freedom, one that acts on the other degree of freedom of the wormhole, and then the matter in the middle. And the only interaction between the matter and the boundary is due to that overall constraint. And we had a similar structure in the SYK model, that we had some degrees of freedom which are roughly like a CFT1. Those were those fluctuations in the directions orthogonal to the valley that we emphasized last time. And then to that we are coupling this is coupled to the Schwarzian degree of freedom, which gives us a translation between some artificial time coordinate that is not gauge invariant, which is analogous to the time coordinates of this ADS space, coupled to the Schwarzian. So this is what we had in SYK. And in gravity, nearly ADS2 gravity, we have a quantum field theory on ADS2, and that's coupled to this boundary mode. So this part is exactly the same, and this is a boundary mode of the graviton. Now, this part in SYK is not equal in detail to a particular quantum field theory on ADS2, so we don't know exactly whether this has some interpretation that corresponds to some object moving in ADS2. But what is true is that we have a sector that is conformal invariant coupled to the Schwarzian degrees of freedom. Notice also that we start, that here we have some Lorentz symmetries here in this bulk, right? Which are the Lorentz symmetries. Well, they are the ADS2 isometries of ADS. Locally, they act like ordinary Lorentz symmetries, and those are exact symmetries in this description, right? They are, but they are a gauge symmetry. They are not directly visible in the boundary theory, and the same is true in this description. So the macroscopic SYK model does not have an SL2 symmetry, but it appears here again as some kind of gauge symmetry. Okay, so that is the end of that remark. Any questions? No questions. Okay. So today we're going to discuss planar theories, so that is, we are going to discuss large n matrix theories. So these are theories whose basic degrees of freedom are n by n matrices, and so they have some Lagrangian that involves some matrices. We're going to consider Lagrangians that mainly have a single trace. We could also think about Lagrangians that have multiple traces. That's somewhat similar. And we could have either one matrix or two matrices or an infinite number of matrices. The important point is that we have matrices and that the matrices have two indices. Simplest case is to consider a Hermitian matrix. Then we'll have these two indices. And so this encompasses a large class of theories, including Yang-Mills theory, for example, where we have the gauge field is a matrix and so on. We could either have a gauge, so this action has a UN global symmetry, and in some cases we might gauge this symmetry, in some cases we might not, but that's not what's important. What's important is that we can classify the diagrams in a certain way. So this is most easily seen by using a double line notation, where you represent the propagator of the matrix with a line that has two indices, the index I and index j of the matrix. And then when you have a cubic interaction, you have these lines meet in this way. So the index I of one is related here, is contracted with the index I of the other matrix, and similarly for the other indices. And then when you write down the diagrams, you can write down, for example, the vacuum diagram. So we have just a particle going on the loop, and this will give us a factor of n squared from the sum over these indices. All these have some orientation, but we normally don't write it. Okay, this gives a factor of n squared. And then if you consider, for example, this correction, then we'll get a factor of g squared from these vertices. And we also have a factor of n, another factor of n, because we now have one extra color loop. Sometimes, these indices are sometimes called colors for obvious reasons, due to the relationship to QCD, of course. And similarly, we can consider these other diagrams, and we again get n squared times a function of this, times g squared n. Now, not all the diagrams are planar, so an example of a diagram that is not planar would be, let's say, in a 5-4 theory, a diagram of this sort, where we contract, so there is a a ribbon that comes out of the board and attaches onto the other side. Okay, so that's not a diagram that we can draw on the board. We have to go out of the board, so it's not planar, cannot be drawn on a plane. We could draw this diagram on a torus, for example. And in this case, we have a factor of g squared n, and there is actually only one index loop, because if you follow this line, you find that this line actually goes around and becomes the other line on the other side. So there is only one index loop. So we see that this term goes like g squared n times n to the 0, right? So it's down by 2 powers from this type of diagrams in the limit that we hold g squared n fixed. So we are going to be interested in taking n to infinity and g to 0, keeping this is the same as what we've done before for the vector models and so on. So this is fixed, and this could be either large or small. If this is small, this is a simple perturbative expansion, and if this is large, then that's the interesting regime that we'd like to analyze. Okay. Now in this case, there is an interesting, a simple argument for why the planar diagrams are the dominant ones, and also an argument that classifies all the diagrams. So if we consider an action with the factor of g written there, and we imagine that we have we have a propagator here, and the propagator is the inverse of this operator. So each propagator will contribute with a factor of g squared. So we'll have a factor of g squared for each propagator. And then we'll have a factor of, so this is the number of propagators. And then we have a factor of minus g squared for each vertex that we have in the theory. And we have a factor of n corresponding to all the color loops, right? Now if we imagine the diagrams, so these diagrams, each, we can think of these diagrams as defining a certain two-dimensional shape, right? Where each of these lines is an edge. There are vertices and there are faces, okay? And the shape does not have to exist in written on the plane. It could be in any space, but we can build the shape this way. And then we would have, this becomes g squared to the number of edges minus vertices times n to the number of faces, okay? And then we can put in a factor of n here and subtract here, we'll add here vertex minus edges. And then what we find here is that this particular combination is related to the Euler characteristic. So is equal to the Euler characteristic of the surface, which is 2 minus 2g. So where g is the genus. So for example, when g is 0, faces minus vertices, well, faces plus vertices minus edges gives always 2, okay? And that is the factor of n squared that we were getting in all planar diagrams. That can be, these are diagrams that, well, when we compactify the plane to the sphere, can be written on a sphere. This is, of course, in the continuum approximation, has this familiar form. This is for a continuous surface. Here is these are discrete surfaces. Okay, so this is the first point, and this neat classification of diagrams implies that when we calculate the effective action, or the logarithm of the partition function, we'll have a term that goes like n squared, that will be a function of lambda, and then there will be a term going like n to the 0 times some f1 of lambda, and so on. So we'll have a series expansion in powers of 1 over n squared. Okay. Now, so Toft originally derived this, and he said, well, this looks very much like a string, like an expansion for a string, right? And so this is the same as, similar to the string expansion, if we think of n as 1 over g string, And we think of lambda as some parameter of on the string bullshit. So the string bullshit theory might have some parameters, and then lambda would be one of those parameters. So that's this is just an argument. There is not more to this argument than this type of this relationship, but it's a powerful relationship. This argument doesn't tell us what the action for the string is, and it's a mystery in this field how to derive in general from this Feynman diagram expansion the actual action for this string bullshit. Okay. Now there are some examples where you can derive the action through either these diagrams are very special and you can find the action, or more generality, maybe you have some guess from some other point of view for what the action should be. An example of the second category would be when you start with d-branes and you have the near horizon geometry of d-branes, then you have strings in that near horizon geometry, and that gives you some strings on some backgrounds, and then the same d-branes have a gauge theory description, and that gives you the diagram. So that's a connection between the diagrams and the but we don't know in general, and some people are of the opinion that the continuous string bullshits are only obtained when lambda is very large, because you need, when lambda is very large, there will be a large number of diagrams contributing, and then all these little triangulations could be viewed as small triangulations of a very, very big surface, and therefore we will get the continuous description only for very large lambda. And that was that's generally the idea about 20 years ago, and I think it might be true. So we don't have an example where we have a continuous description for arbitrary lambda or even very small lambda. Okay, and people have been trying. People think, well, the generalized opinion about string theories is that the continuous string description should exist for any lambda. It might be a weird string bullshit, but that it should exist for any lambda. But very explicit, explicit constructions where you put them in the framework of ordinary string theory, or maybe generalize the framework to something that would be valid for arbitrary lambda is something that is not known. Now you can say, well, people that are doing integrability, like Pedro, for example, will tell you what the answers are for this string theory for any value of lambda, and so but these answers are not obtained by taking a particular string theory and quantizing, but by using bootstrap techniques. So you assume that some kind of theory exists, you put it in some like gauge, and then you do the computation. So if you want a challenging exercise, just find some method to take any large n gauge theory and find directly a some kind of two-dimensional description. May not be solvable. Maybe it's a numerical method that only works in 2 dimensions, but a method where n is not the number of fields, but n is a parameter, right? It's the coupling of the bullshit. So where n has disappeared from the story. Finding something like this would be very useful. Even if it's some numerical technique, or maybe some technique using tensor network, some clever technique, maybe will exist. I think it should probably exist. This type of argument suggests that it should exist. It's just one of the things that hasn't been done yet. Okay, so I would say the most interesting application of this idea is the application that suggested the idea in the first place, which is the application for explaining the strings that actually exist in nature, which are the strings of QCD. Okay, so strings of QCD are experimentally observed strings. Okay, so when people tell you that strings do not exist, you can tell them, wait, I think they're in the, they exist. They make them in the accelerators. Okay. So our current picture for these strings, the picture in terms of QCD, is that somehow, due to confinement, the color electric fields that normally for point charges spread everywhere, they form narrow tubes, and at long distances they behave like some kind of string. Now, if we analyze this problem at large n, we would have diagrams So we have quark lines. So a quark line is a diagram which in this double line notation is actually a single line. Okay, and then so if we have the force between two quarks, it would be described by the exchange of a gluon. And then if we have corrections to this, we add other gluons and so on. And to lead in order, we get the planar diagrams with two endpoints. So we get something like an open string. And the idea is that in the large N theory, these strings, the strings that appear in this argument should be related to the strings that appear in QCD. And furthermore, this argument suggests that those strings would not break. So the probability for breaking one of the strings would be 1 over n. And so that suggests that in the large N limit, these strings would not break. In QCD, they do break. Now you can say, well, what is a good evidence for these strings? And one that looks very direct and simple is to plot the mesons. So take so this plot is usually plotted as you plot the mass square of the mesons, and you look, let's say, at the mesons that have the largest spin for the lowest mass, or the lightest mesons of a given spin. And what you find is, well, the possible spins are, let's say, 1, 2, 3, and so on. And so around here you have the raw meson, and then you have a bunch of other mesons. Have some F2 meson or whatever. So you have all the various mesons here. And they form a nice straight line. Well, this is not straight. This is not experimental data. This is my memory. So my memory is imperfect. Of course, these mesons have some width and so on. The width is about 10%. So that suggests that they are not, well, they have a reasonably long lifetime. So that suggests that maybe n equal to 3 is not too different from large n, from n equal to infinity. And that maybe the idea of thinking of 1 over 3 as a small number might be reasonable. After all, it's 1 over 3 squared. That's not so small. And maybe there might be factors of pi or whatever. But well, 1 over 3 squared gives you the decay width of these particles. Now you laugh, but it's well, and a point that Ed made in his large N paper was that when you think about alpha, so the charge E of the electron is actually 1/3. So in QED, 1/3 is a good number. And so maybe the factors of pi might work out so in your favor. But I think regardless, you can look at nature and decide whether the coupling is small or not, right? So what is the signature of small coupling is that if the coupling was exactly 0, these particles would be exactly stable, right? They would take forever to decay. But if the coupling is weak, you will, if it is weak, well, they will have some width, but the width will be small compared to the mass, okay? And this is indeed true for these particles. It's not super true. I mean, it's about 10%, but it's pretty good. And this plot goes about to spin 6 or 7. Okay. So those are the strengths in nature, and not only that, but actually the models that model hadronization. So when you have a collision in the LHC and so on, you have some models that describe the hadronization process. So that is what happens when a quark and an anti-quark or any colored particle separates, and you get these colored lines, and these lines break and so on. They use sort of this picture of the string. It's called the Lund method and so on, and it's buried within the simulators of LHC collisions. So it's not only that the strings exist, but they are actually used in the theory, in describing the data. They are used and all that. Okay, with all those things said, we should issue an apology, which is the fact that after I don't know how many years, that's from 74, so a huge number of years, we still don't know what the, we don't have a description or a well-sheet description of the QCD string, of the large N QCD string. So large N, what I mean is large N Yang-Mills theory, okay? So just forget about the quarks. The idea is first you would solve the large N limit of Yang-Mills theory, just the action trace F squared. This action is of the form of the actions we discussed in the very beginning. And yeah, so well, what do we expect? So let's say a few words. So we can, this action of course has a beta function, and an interesting thing is that the beta function has a nice Larsen limit. So if we define this as the 't Hooft coupling, then the beta function for the 't Hooft coupling is a function of the 't Hooft coupling. So it's not 1 over n suppressed or anything. Okay. So we expect that the 't Hooft coupling would be very weak. So we would have as a function of energy. So at very high energies we have 't Hooft coupling which is very small, then logarithmically it runs and becomes very strong, and at some point it becomes of order 1, okay, at the scale lambda QCD of the Larsen theory. So that this is defined to be the scale where this becomes of order 1, and here the theory is expected to be confining, and so we expect to have it's expected to be confining, and the masses of glue balls would be of this order, and the tension of the string is also expected to be of this order. So that's in for the string of Young-Mills. Okay. Now, so when this idea first came out, so people said, okay, let's imagine that this is a string that moves in 4 dimensions, and it turns out that the string in 4 dimensions cannot be consistently quantized, okay, in 4 flat dimensions. And the minimal thing you could do is to add 1 extra dimension. So one idea that is around is the idea that this should be a string that lives in 5 dimensions, but in some space that maybe has a warp factor as a function of an extra coordinate. So some 5-dimensional space of this form, where the extra dimension would be roughly related to the thickness of the of this color flux. So a string that is very close to the region where W becomes very large, which we call the boundary of the space, would be color electric fluxes that are very thin. But the idea is that in this extra dimensional space, the string would be infinitely thin, like the strings of ordinary 10-dimensional string theory, or any string theory, but that their position in C gives them a thickness once you translate them to the 4-dimensional picture. Now we don't have this story for ordinary Young-Mills, but of course we have the story for a supersymmetric version of n equal to 4 super Young-Mills. So this is the same theory that we had here, so same action, plus some matter fields, okay, that are in the adjoint. So they're all in the adjoint, and so they're also matrices, and their interactions, self-interactions, and so on, and the precise matter content is such that we have n equal to 4 supersymmetry, so the maximal amount of supersymmetry. And in that case, this space we were talking about is ADS space. Okay, so I won't review this anymore. I'm going to now, because probably you've seen that before, so I'm going to review an interesting some older topic, but that maybe it's probably less likely you might have heard about it, and it's the topic of matrix integrals. Okay. So given the fact that it is difficult to sum planar theories in general, you would hope to find a simpler setting where you can actually solve the problem and at least learn some perhaps more general lessons. Okay, and that setting is you set d equal to 0 in the action we had before. So what we will be doing is we're going to be considering an ordinary integral over a matrix. So here we have n squared integration variables, e to the minus 1 over g squared trace of v of m. And we are imagining a v of m, which is, let's say, m squared plus then some coefficient, let's say, alpha m cubed, and so on. Maybe there could be different powers. When we write the action this way, these parameters alpha are already 't Hooft-like coupling constants, and well, g squared n then would be another 't Hooft-like coupling constant. sometimes people write directly here this as a factor of n, okay, times potential of this form. That's also equivalent to this. So now, so we have this, and we can now look at the Feynman diagrams of this. So we'll have the same diagrams we discussed before, but there is a nice simplification because now the propagators are just one. There is no p squared, there is no momentum integration variable, there is nothing like that. And so all that we have are the vertices and these diagrams. And therefore, this simple matrix integral, for us, what it is doing is really counting the number of diagrams that we have. So each diagram will contribute with a factor which is, well, it's proportional, again, to those factors we discussed before. So g squared n to the number of faces minus 2 plus 2g. So this is just a rewriting where is the formula is over there. I used, again, the Euler number times n to the 2 minus 2g. Okay. So we have the diagrams of each topology, and then for each phase, we have basically a factor like this. So that's if we were to set alpha equal to 1, right? And we just have the cubic theory, for example, then we have exactly this. If we have here more couplings, then we are weighing the diagrams differently for different vertices. So this is, but the basic idea is the same. So notice in particular that we could think of this as a term. So let's say, for example, genus 0 here. So this term could be viewed as roughly going like e to the, well, if we define, well, f is the number of faces. If we imagine that each phase we assign it an area, let's say 1, okay, of, we discretize a very big surface in units of 1, then this term would be a bit like a cosmological constant. More precisely, if we define this whole thing to something which could call the Bayer cosmological constant, then we have e to the mu Bayer times the number of faces, okay? And this is the area of the surface. So this is a way to think about, let's say, a two-dimensional theory of quantum gravity, where you discretize the surfaces, and then you're weighing the surfaces with this cosmological constant. Now, in general, there will be minus signs here, because if we have exactly literally this with a +1 here, we would get a minus sign for each vertex when we bring down this vertex from the exponential. So in order to have actually discounting with positive numbers, we should have a minus sign here. So this is a potential which this is a potential like this. And we are doing a perturbative expansion around this point. So the full integral, either you have to shift the contour of integration and so on to make sense of it, or if you think of it as in terms of this contour, you're just doing a perturbative expansion around this point. Okay. Good. Okay, so that's this is a motivation to study these matrix integrals. I mean, there are many other motivations to think about this problem. One was just to simply count the number of diagrams. The other is just understand generically large n-planar theories. And then these matrix models have a surprising range of applications. So you can just think that another application of this is to think about this as follows. So you can think of M perhaps as some matrix that appears in your problem. Maybe M is the Hamiltonian of your system. And then maybe it's random, you don't know it. And then you assume, well, maybe it's given by a Gaussian distribution. So that's one application of this. But there are other applications in condensed matter where M is some other random matrix that might appear in your problem, maybe some transfer matrix of some problem, and so on. And so you might, for many reasons, be interested in studying random matrices where the probability is, so here we have a more or less uniform probability for each matrix element. So if we take, for example, the Gaussian, we'd have a Gaussian distribution for each matrix element. And okay. And often what we're interested in is understanding the distribution of eigenvalues. So in fact, this discussion of eigenvalues arises naturally if we want to actually do this integral. It's convenient to diagonalize the matrix. Okay, so this is a diagonal matrix of the form lambda 1, lambda n with zeros, and U is a unitary matrix. So if M is Hermitian, we can always do this, and so we can change variables. So this is the first step. The second step is in the of course, V, so after this step, V of M is equal to, well, V of M, not trace of V of M, is equal to trace of the diagonal part, which is just the sum over V of lambda I. So in other words, the term in the exponent depends only on the diagonal part and not on the unitary. So is this familiar to all of you? Or? Yes. Okay, familiar to most of you. Okay, maybe I'll just skip it. Okay, so you get a van der Monde determinant, delta lambda I, which has a form lambda I minus lambda j squared. Well, maybe I skip all of it. Okay, let me ask you, why do we have this factor? Let me just explain conceptually one point that is important. So we have here that the distribution goes to 0 when two eigenvalues become close by. There is this eigenvalue repulsion. It's important to understand conceptually why it is arising. Okay, it's not just a mathematical thing. Oh, I do some black box. I have to look in the math book and so on. There's a simple reason, and it's the fact that if you have a generic matrix and you are trying to make two eigenvalues coincide, you need to tune three parameters. Naively, you might say, if I want to make two eigenvalues coincide, I need to tune just one parameter in the matrix, right? The two eigenvalue, one eigenvalue equal to the other, right? But you can understand that this is not the case by simply the example of 2 by 2 matrices. Take them to be traceless so that we get rid of one trivial one, so that the sum, we take the sum of two eigenvalues to be the same, right? That's a trivial overall degree of freedom. So we have a Hermitian matrix. We have 3 parameters in the matrix. In order to make the eigenvalues coincide, we need to tune all 3 to 0. Okay, so here the eigenvalues of this matrix are lambda plus minus square root of a squared plus b squared. I mean, this fact appears all over the place, and it's a useful fact to remember. So, and this is the reason why we have this factor of lambda I minus lambda j squared. This is just that we have a 3-dimensional space, and in this 3-dimensional space, the radial, the 3-dimensional flat metric becomes dr r squared. R squared is lambda squared, lambda I minus lambda j. And we should have that for each factor, so we have this product for all pairs. Okay. Good. Now there is another place where this appears that maybe, well, this remark is useful for something else. Imagine you have bands. Let me, it's something completely different, but just to help you connect different things. Suppose you are a condensed matter physicist and you're interested in electron bands. So you have the bands of free electrons. So you have an electron hopping in a crystal, and you have these bands. Then you can ask, when do bands cross? So is it possible for 2 bands to cross? Okay. Now, the bands are some energy levels, and they are functions of momenta, right? So there are very small. So you can have a band in, let's say, 1 dimension. It will be a function of just one parameter. And a generic band that is given by diagonalizing some Hermitian Hamiltonian will not cross because we don't have 3 parameters to tune. But if we have bands in a 3-dimensional material, then we have 3 momenta, and if the system has no special symmetries, so no time reversal symmetry and so on, so that the Hamiltonian you are diagonalizing is a Hermitian matrix, then you will need to tune 3 parameters. That means that band crossings in 3 dimensions consist of points, right? Sometimes called Dirac points in metals or Weyl points and so on. So that's the reason why they arise. Okay, so it's the same as this story. So it's not, this factor is not just a mathematical little trick. It has an interesting physical significance. Well, or if you watch it, some interesting mathematics, but it applies to many aspects. Okay. Good. So the matrix. well, maybe if you all know this, maybe I should just not go through it. So, have you all heard about the eigenvalue distributions and the equation for the eigenvalue distributions? Okay, so we reduce our integral to just integral over all the eigenvalues, delta of lambda e to the sum 1 over g squared b of lambda I. Okay. Now this delta can also be written in the exponent as log of lambda I minus lambda j squared, sum over I and j. And you can think of this as a statistical mechanics problem where you have a potential and then you have variables that repel each other with this logarithmic interaction. So they will reach some kind of equilibrium where this repulsion from the eigenvalues is balanced by the potential, right? So if indeed you could imagine saddle point equations for this problem, where you would have so that equilibrium would be described by saddle point equations of this form: sum over j, j different from I, of 1 over lambda I minus lambda j. And often people start from the saddle point equations and then make a continuum approximation. But it is conceptually wrong to think about the saddle point equations because we're going to be interested in a regime where the fluctuations around the saddle are actually bigger than the distance between the eigenvalues. Okay, so but this is at least to orient. The picture I mentioned before of these things finding an equilibrium, the equilibrium would be this. But we're going to be interested in a regime where the fluctuations are a little bigger. But fortunately, something we can do is we can define, let's say, imagine thinking about the density of eigenvalues, sum over I of delta of lambda minus lambda I. And then we approximate this by a continuous function, right? So it's a sum of delta functions, but we're going to approximate this by a continuous function rho of lambda. And eventually we will find that this function will be non-zero in some region of lambda space and 0 outside. We don't know that yet, but this is what we'll find. Okay, but if you make this continuous approximation, then you can rewrite the action that we had as so somehow here we'll have some integral over all the lambdas. Instead of integrating all the rows, instead of integrating over the lambdas, we'll do an integral over all possible rows. If we restrict it to rows that are sum of the delta functions, that will be equivalent to what we had before. But if we have continuous general rows, that's something slightly different. And then we have n squared integral. So we have a term that goes like d lambda prime, rho of lambda prime, log of lambda minus lambda prime squared. And then there is a term 1 over g squared. This is just an integral over 1 lambda times n d lambda rho of lambda. So I pulled out one factor of n. Because of this n, there was a factor of n squared here multiplying this term. Here there would be only one factor of n, and I divided by this. So now we have the Toft coupling here. And then there is a term I mu integral lambda minus 1, rho of lambda minus 1. This is just enforcing the condition that the integral d lambda of rho of lambda is equal to 1, which follows from this definition. Okay, so this is a normalized distribution. Okay, and the nice aspect of this action is that we have n squared sitting out in front, and so we are back to the story that we discussed with ON and SYK and all similar stories, where we have now some function of one variable. So we start notice that the initial integral was integrals over just numbers, okay, in 0 dimensions. Now we have something that is a bit like a one-dimensional field. So we have an extra dimension, which is lambda, we're integrating over fields defined on this extra dimension, but this field will be classical in the large N limit. Okay, so this is the variable that becomes classical in the large N limit. It's an average over the eigenvalues. Okay, so that's will be the variable that becomes classical, not the eigenvalues themselves. This rho of lambda. So here the eigenvalues are sort of jiggling and fluctuating at very short distances, and they are defining a smooth distribution. Yes? The last term is a Lagrange multiplier that enforces this condition. Okay? It's not very important, so if you can see it, it's good. Yeah. Yeah.
Where does V appear in this equation?
Where is?
Should V be in this equation?
V. Oh, of course I forgot V. V is here. This is important. Yeah. So V. So this term is just simply that term over there, the term in the right-hand side, and this came from the. So we have this classical action, the eigenvalue repulsion, and then the potential. Okay. And now we just look at the classical equations. So that's similar to things we've done a few times already. So it's a simple okay, so so what are the equations? So we calculate the equations and we find minus, let's say, well, from now on I'm going to well, the equations are like V of lambda plus integral d lambda prime. So this is after taking the derivative. Now factors of 2 I'm probably going to get wrong. But, okay, so we have this equation. This is integrated over lambda prime, and then for all lambda, this should obey as long as lambda is in the support of rho. Okay, so so this equation is supposed to hold only within the support of rho. So this is a small technical detail. Now we can get rid of this by taking the derivative with respect to lambda, and so we get v prime of lambda plus integral d lambda prime rho of lambda prime over lambda minus lambda prime, and the proper prescription for this pole is to take the principal value, so principal value equal to 0. Okay, so that's the equation, and this equation has a nice physical interpretation. It's saying that the force due to the potential should balance against the repulsion due to the other eigenvalues. So there are eigenvalues on one side pushing one direction, the other side pushing the other direction, and that force should balance on each eigenvalue separately. Okay, so now if the potential is simply lambda squared over g squared, then that's the Gaussian case. Then you can check that a rho of lambda, which is given by a semicircle distribution, 1 over the maximum lambda squared, square root of lambda minus lambda maximum all square, with the lambda maximum proportional to the Toft coupling, or just this number. This is just rescaling. I mean, we could have removed this by rescaling lambda, but so we find the distribution of the promised form. So we have lambda, and then we have some maximum lambda minus lambda maximum, and then a nice semicircle distribution. Okay. So that's what you get for a Gaussian potential. So for when each of the matrix variables is a Gaussian random variable. So that's the average distribution, and then people have analyzed this problem much further, trying to understand the correlations between different eigenvalues and so on. And for some problems, it's more interesting to find the correlations between eigenvalues, like for example, if you are studying the original problem. So this is called Wigner semicircle law, and the problem that Wigner was considering was thinking about nuclear energy levels, and he was thinking, well, let's say the Hamiltonian is a mass, so it's a random matrix, and then he found this distribution, but he wasn't saying that this distribution was the distribution of energy levels. What he was saying is that the spacing between the eigenvalues that we haven't derived, but we could derive using similar methods, is the statistics of the spacings will be similar to the statistics of the spacings in the nuclei. Okay, and so that's some distribution of spacings, which goes to 0 for very small spacings due to the eigenvalue repulsion, and then it grows up to the average spacing and then goes down. Okay. Good. So that's for the simplest Gaussian model, and for that model you can just check this equation directly. For more complicated models, there is a technique. There you have to use some tricks. Okay. And this problem has been around for a long time, and people developed lots of tricks to solve these problems. I'm not going to discuss the most sophisticated trick. Some trick that sort of with intermediate sophistication, let's say. And a trick that proves useful is to define an auxiliary function called the resolvent. It's because it's going to allow us to solve the problem, which is defined as rho of lambda, lambda minus lambda prime, and this is an integral over the support of rho. Okay, it could be one interval, it could be many intervals, and so on. So that's this. And now we use, in the words of Schwinger, the greatest discovery in theoretical physics, which is the complex plane. Okay. So we have this function will have a cut between A and B, and will be analytic everywhere else. It goes like this function will go like 1 over lambda for lambda going to infinity, and so on. Okay, so that's a resolvent, and what we're going to do now is we're going to derive an algebraic equation for the resolvent. Okay, so this integral equation that we have over there, which looks like a complicated integral equation for rho of lambda, will translate into a simple algebraic equation for the resolvent. Okay, so that's what we are going to do now. How do we do that? Well, again, you have to be inspired and find the right trick to use. So you integrate the appropriate quantity. So since we want to use the resolvent, it looks kind of promising to start with some integral of this kind. Then we'll eventually use the equation, but so far we are not going to use the equation. So we start with this. This is not equal to the resolvent. This is some other integral that we could have. So it differs from the resolvent because we have this v of lambda prime here. Okay. And then what we do is we add and subtract v, v of lambda prime minus v of lambda over lambda minus lambda prime. Okay, v lambda prime. And then there will be a term where we have just the v of lambda. But v of lambda is not an integration variable here. We just pull it out of the integral.
Well, in the first term you have v prime of lambda.
Oh yes, v prime. V prime this is the time derivative. Sorry, there are too many primes. But the point is that maybe I should. Is it clear to everyone that we get this, and then the integral that remains is the resolvent, right? Okay. Let me say this the following way. If this was a v of lambda, we could pull it out of the integral, and we'll get the resolvent. Okay. Since that's not what we have, we subtracted v prime of lambda, and now we have v prime of lambda times the resolvent. But this function here has a nice property. So if v is a polynomial, then when we take a difference of these two polynomials, we can cancel a factor of lambda minus lambda prime, and so this integral has no singularity at all. It's just the integral of some polynomial, and so that's a magical. Well, that's a completely analytic function. It's just a polynomial of lambda. Okay. So we don't know the coefficients, but this will give us a polynomial of degree n minus 2 in lambda, where the v, so the degree of v is n. Okay. So n is by definition the degree of v. So we get a polynomial of some degree. Okay. So this contains coefficients we don't know. We'll determine those coefficients later. Okay. So that's half of the argument, and the other half uses the equation that we had over there. And so notice that v prime is sitting in that integral, so we're going to replace the v prime using the equation. Hopefully I didn't erase the equation we had there, right? So this is equal, so let's call this the left-hand side. So this is the left-hand side. So the left-hand side is equal to an integral d lambda prime rho lambda prime. And then we have a rho lambda double prime, and we had lambda minus lambda, so times 1 over lambda minus lambda prime, and then 1 over lambda prime minus lambda double prime. Okay. What I've done is use that equation, but I've said I changed lambda to lambda prime and lambda prime to lambda double prime. Okay. So that's what we have in the left-hand side. And now we can rewrite this. So first we notice that this factor is symmetric under exchange of lambda and lambda prime. This factor is not quite symmetric under lambda change with lambda prime, but we can take this and add the symmetrization of that, right? So we have, what's the nicest way to write this? So we have 1 over lambda prime minus lambda double prime, so that's this factor. And then we have 1 over lambda minus lambda prime, that's this factor. And now we add the symmetrization of this factor. Okay, so symmetrize here, we get the minus sign, so we get the minus 1 over lambda minus lambda double prime. Okay. And now we combine these two, and we get, so that's equal. So we get the lambda prime minus lambda double prime in the numerator that cancels this, right? And the net result is that this gives a lambda minus lambda prime, lambda minus lambda double prime. Okay. And miracle now. So these two factors, now the integral factorizes into two integrals. Okay. And each of the two integrals is equal to a resolvent, right? So we have the resolvent of lambda squared. Okay. And now we've got the equation that we wanted. So we have an equation which says, let me write it in this blackboard. We have now an algebraic equation for R of lambda. What's the equation? So the left-hand side had given us R of lambda squared, and the right-hand side has given us b prime of lambda, R of lambda, plus some polynomial of lambda. Okay. So what do we know here? We know v prime. We don't know this, but it's a finite lack of knowledge. There are only a few coefficients here we don't know. And so we basically know this function, right? So we can, we get the function. We can rewrite this equation. Well, maybe I won't do that. Yeah, I won't do that. So this equation is just a quadratic equation, so there will be a square root in the solution. And roughly speaking, the terms inside the square root will have a v prime over 2 squared plus this polynomial n minus 2, right? Or let's say v prime squared plus some other polynomial, okay? We know this. This has some relatively high degree compared to this one, and this we don't know. And we have a square root. So we said that the function the function resolvent would have some kind of branch cut at a and b. And now we know that all those branch cuts are going to be square root branch cuts. Okay. Good. Now, if we, so here we have something like minus v prime, and so on. So when we expand for large lambda, it turns out that requiring that R of lambda goes like 1 over lambda fixes one of the coefficients in P. Okay, we're still left with n minus 3 coefficients to fix. And those n minus 3 coefficients correspond to various cuts that we can have, the positions. Okay. When we have a complicated potential, let's say we have a potential like this, we can feel various minima of the potential, right? And so we have the option of filling this a little more than that one, and so on, and solving the equations. And how much we fill each one is contained in the parameters that remain in the potential. Okay, so you can do a counting. Now, in the case that we are interested in, or we might be interested in the case that there is only one, that we have a potential like this, as the type of potentials with negative coefficients that we discussed were kind of relevant for this problem of defining 2D quantum gravity, right? Then we are interested in filling only one thing. But if we fill only one, means that there is only this polynomial. There is a term, so this full thing inside the square root has a term lambda minus a, where a is some number, lambda minus b, where b is some other number. And then the rest are lambda minus lambda minus ci squared. Okay. So we have to come up to the overall degree of this, which is 2 times n minus 1, right? Which is the degree of this thing. And it's not any polynomial, but one that has a bunch of double zeros, right? So that when we take the square root, this does not lead to extra branch cuts, right? We have a single cut. And the condition that all these zeros are double fixes the rest of the coefficients in P, okay? So we've solved the problem completely. It fixes all the coefficients in P. A and B and C and so on are fixed in terms of the parameters of the potential. Okay? So that's the solution of the problem. And all of this is fixed with some algebraic equations in terms of the parameters of the potential. And once we have the resolvent, or we could, if we wanted, we could calculate rho by calculating the discontinuity, which will be related to this square root here. And that determines rho of lambda. And once we have rho of lambda, we can replace it in the action. And so in this action here, this is a kind of Gaussian integral. So when we can replace it either in this term or that term up to some factors of 2. And in this way, we calculated the action. And yes.
If I have two parallel cuts, both of them which have eigenvalues, and then they collide, I don't expect them to disappear. But I'm a bit confused by the eigen. Because I have just two cuts that are parallel.
Yes. So yeah, you can have something like this, right? And then this is how they can two cuts collide. Well, these cuts are supposed to be on the real axis. So we are because we. Well, they don't. Okay, so then that's a complex thing that. Well, okay. If we are interested in this, for the problem we're interested in here, which is to do these Gaussian integrals that we were discussing, and on the main contour and so on, where we are talking about these eigenvalue distributions, these cuts will be on the real axis, okay? Because that was basically the defining property of R, is that this rho of lambda, when rho of lambda prime is on the real axis. This is from the very beginning. Now, it might be that you start with this problem and you start analytically continuing in the parameters, and then the cuts might be somewhere else, and in some applications they are somewhere else. Yeah, maybe some other phenomena can happen, like what you're discussing. But the phenomenon that can happen is this combination.
I thought it was generic. Whenever the potential had a maxima, I thought the eigenvalues would be imaginary and perpendicular to the maxima, and when they have a minima, they are real.
Yes. But well, it would be unphysical to try to expand around this maximum, put the eigenvalues around the maximum. So in a situation like that, we would take these two cuts, fill them, and we are discussing these two cuts. Of course, this is a situation where we have a branch. We have these two branch cuts, right? Now you can say, well, I don't want to run the branch cuts this way. I want to run the branch cuts that way. You are free to do that mathematically, but the one that has the simpler physical interpretation is the one where you...
We have the discrete equation, right?
What?
We have the discrete equation. It will tell us where to put the cuts in this case, right? We can find the position of that.
Yes. So if you, yeah.
Be a prescribed
Yeah, so that will give you, yeah, in some situations that could, yeah, that equation could in some cases have some complex solutions. I agree. Okay. Yes.
I don't put the data lambda as exponent node, rather I use ghost field and then place the action. And I integral lambda first and finally solve the ghost field. Can we get the same final answer as you
I didn't understand the alternative method. Could you repeat what?
Okay, so you put the data lambda as exponent node stuff, right? If I don't do that, I just introduce two ghost fields.
To what kind of field?
Ghost field.
Ghost fields. Where could you go back one step? I didn't understand.
I just want the measure factor into the action. And
Yeah, that's what we did. That was the delta, right?
yeah,
Yes.
yeah. So I use a different way. I introduce two ghost fields and put this into the action.
Yes. Yes.
And
Yes. Yes.
I integral lambda first and finally solve this ghost field. I just wonder whether we can get the same answer like you do.
I feel that what you would need to do is first integrate the ghost. So the ghost field is a Grassmann variable. I mean, using ghost is one way to derive this factor. So it's a Grassmann variable. You integrate it, then you will get this, and then you will get the term that we discussed. I don't know how to solve this. I'm not sure it's possible. I don't think it's possible to solve it by finding classical solutions for the ghost field because it's a Grassmann variable field. Okay, so at this stage, what we have is that log of z is n squared times times some function of the parameters in the potential, right? This g squared n and so on. Okay. Now, just for example, we can consider this potential where we have m squared plus g squared n m squared m to the fourth, right? Okay, so let me call this parameter g tilde squared. And I said we want to put it with a minus sign. Well, let's first put it with a plus sign. Remember, this g tilde squared can be negative. Okay. This is more conventional. Now, the first point is that when you solve this, you find so that for very very tiny g tilde, you will find this this eigenvalue distribution, and for relatively small g tilde, all the equations that you solve are algebraic equations that can all be expanded in series. Everything will be analytic in g tilde. Okay, so in fact, this action is this whole action is analytic in g tilde around g tilde equal to 0. So that means that the series, the perturbative series in g tilde, has some finite radius of convergence. Okay, this is unlike ordinary perturbation theory, which has a 0 radius of convergence. Okay. You can ask why the Dyson argument doesn't work in this case, but I leave that for the question period. Now, however, if you start making g squared negative, so this is g tilde square equal to 0, we said it's analytic and we naively expect it to be perfectly fine for positive g squared. But when we take it to negative g squared, there is some critical value, g tilde critical. And at that critical value, what happens is that we are starting to fill these eigenvalues, and they start to spill over the barrier. Okay, and so that's the physical interpretation. Mathematically, what happens is that this function that will have a singularity, and it will be some square root branch. I mean, some branch cut singularity, because we are solving just all these algebraic equations. The worst we can have is this branch cut singularity. And indeed, if you do this, you find that this function has some analytic pieces, and then a piece that goes like g square minus g tilde square critical to actually the power is 2 plus 1/2. Okay. So it's a square root branch cut singularity. Now, the interesting observation is the fact that this singularity can only come from an infinite number of diagrams. Okay, because for any finite number of diagrams, we have something analytic in G, but when the number of diagrams becomes infinite, then that's the only place that could give rise to a singularity like this. So the details of this singularity and this particular power and so on, they come from an infinite sum of diagrams, right? So you could say that it comes from the continuum limit of this 2D quantum gravity theory. What is that continuum gravity theory? Well, we said it should be some integral over two-dimensional metrics, and it should have some action which contains a cosmological constant term, because we argued that one of the parameters we had in the action was counting the area of surfaces, so that looks like a cosmological constant term. And so we can try to quantize this action. I mean, we could add an Einstein term if we wanted, but that's a topological term. We could add it, that's no problem. But we have basically this action. And the idea is, if you try to integrate this action, we would choose conformal gauge. So we take G equal to e to the phi times a flat metric, alpha, beta, or the metric of a round sphere. So then this term in the action, so this is of course integrated over space. So we have a term that goes like mu e to the phi. And then we fix the reparametrizations. That gives rise to some cost determinant and so on. And that's the sometimes called Liouville action, which in conformal frame has the form, does depend on phi through the conformal anomaly. And so we get a term that is phi times, let me call this a metric, background reference metric, which could be the metric of the sphere. So we get an action roughly like this. So we have this that comes from the conformal anomaly, plus of the ghost terms, plus this cosmological constant term. Okay. And it's all, this now should be viewed as, this is sometimes called the non-critical string theory, so string theory in 0 dimensions. But more precisely, you should think of this as a critical string theory on a non-trivial background. So on a background that has a linear dilaton, and so the coefficient here is such that the total central charge is 26. And here there will be also coefficient alpha that makes sure that this has dimension 1. Okay. So it's a completely defined theory. It's defined by these two conditions I just mentioned, and so on. Okay. Now, we mentioned before that what we were calling G square n, we later called G tilde squared. That was roughly like e to the bare cosmological constant. And so this parameter that appears here, so we expect that the full expression has some singularity as a function. So when mu bare is close to a mu bare critical, right? We are developing this singularity. That's the same. That is the same as this equation, as this difference. So when so we should identify this parameter mu that appears here with mu bare minus mu bare critical. Okay. And then in this continuum string theory, we can calculate the dependence of the partition function on the cosmological constant. Okay. So we could calculate the sphere partition function, so the S2 partition function, and the S2 partition function of this theory should agree with the log of that C that appears there of the full model divided by n squared, right? So the leading term. So that's what I was calling before F naught. Okay, so F naught should be equal to this. And by adjusting the coefficients in the way I mentioned, so making sure that the central charge here is 26 and this has weight 1, you can calculate what the dependence on the cosmological constant is, and you find that the dependence here matches this dependence that you have over there. I won't go through the details, but so it matches this dependence. if you want more details on this, you can read the paper by Douglas and Schenker. Which discuss this whole story in great detail. But I just wanted to mention this particular application of matrix models, which well, was something quite popular in the beginning of the 90s, and from which a few lessons were learned. For example, the existence of D-branes and so on was importantly understood from this story. And one other point is that is interesting, and well, was also pointed out in these papers, is that is the following: that well, maybe there is one more thing I need to say, which is that so generically the eigenvalue distribution has a square root branch cut at the endpoint of the eigenvalue distribution. Okay. When you approach this critical point, the eigenvalue distribution goes to 0 near the endpoint. So this was going like square root of lambda, and here it goes to 0 like a higher power of lambda. Let's say lambda to the 3/2, right? And that eventually is related to the singular behavior there. So it's something where the behavior near the endpoint is not generic. Not generic, but somehow when you approach this special value, this fine-tuned value, you get this. That corresponds to the situation where one of the zeros here is colliding with one of the endpoints. Okay. So everything, at least from this point, everything has to do with the endpoint of this eigenvalue distribution. So the critical behavior comes from the endpoint. It's not the dominant behavior of f naught. So notice that this is a positive power. So there are other terms here in f naught that are more important. Okay, so not the more important one, but it's the one that is not analytic. So if we were to start taking derivatives with respect to g and evaluating near gc, this term will lead to terms that blow up, while these ones would be perfectly fine. And indeed, to do these computations in string theory is also useful to take derivatives with respect to mu, so to calculate this sphere partition function. It's actually not easy to calculate the sphere partition function directly due to the facts I was mentioning before. Also, string theory is not very well defined. But if you take the cube derivative of the sphere partition function, then that's given by the correlator of 3 insertions of the e to the alpha phi, 3 factors. And that's just a 3-point function in string theory, which is perfectly well, which you can calculate with no problem. Okay. Anyway, so so we said that the leading term here was singular, and it was found that also the subleading terms are singular at the same position. So this also has a singularity in the same place, and this f2 also has a singularity at the same place with particular powers of g minus gc. And the particular powers are such that you can approach the singularity and take n to infinity in such a way that all the terms in the series are kept. Okay, so you can get a full interacting string theory, so all the genus expansion from this, and it all comes from looking at the details of what the it's all related to the details of the endpoint of the eigenvalue distribution. So these are sometimes called the double-scale matrix models. It's called double scale because we scale both g to gc and n to infinity. Okay, but some people quibble with this name. They say, well, it's just one scaling, just 2 variables. It's a complicated scaling. Anyway, okay, and sorry, we are 1 minute over. Yeah. Okay, I'm a few transparencies below. Nah. Well, one final point I wanted to mention is I mentioned it last time, but I was just mentioning that there is a more sophisticated technology that, given the shape of this curve, the shape of the eigenvalue distribution, of the classical eigenvalue distribution, you can calculate all the 1 over n corrections. There are all the 1 over n corrections you would have in a double scale matrix model that has that classical eigenvalue distribution. And this was applied by Schenker, Sad, and Stanford with the input eigenvalue distribution with sinh square root of lambda and with some e to the s naught, let's say. And input in this, you get the whole series expansion in powers of the inverse of this that matches results in another 2D theory of quantum gravity, which is the JT theory of quantum gravity. Okay, so you should think of this. So I gave you two examples of matrix models that are related to 2D theories of two-dimensional theories of quantum gravity. One was related to this Liouville theory of quantum gravity. Okay, and that was the simplest sort of double scale limit. And then this would be a more complicated double scale limit where we put a bunch of zeros here together in such a way that we don't have a single power, but we have a whole sinh of lambda. Okay, so I think I'll end there, and if there are any questions, I'm happy to answer. Yes.
Yeah. Would you mind just elaborating on like the intuitive reason for why here the singularity in this matrix model is at negative g squared, and like the difference is
Yes. Yeah. So first of all, for positive g squared, right? So we have a potential that goes up. We don't expect a singular behavior. Okay. So the fact that singularity is for negative g squared, I think it's clear. Maybe your question is why it is analytic. Why it is analytic around 0? Okay.
why it's not at 0.
Why it is not at 0? Yeah, good. Thank you. Thanks for the opportunity to. Well, first we have to, so to give a nice argument, we have to first recall why for ordinary perturbation theory is at 0, right? Well, let me give you two arguments. The first argument is consider a simple integral like so if we take g positive, this integral is convergent. G squared positive, we take g squared negative, the integral is divergent. So it's not well defined. So that's so therefore this has a singularity at g equal to 0. Now Dyson gave a general argument that is actually very nice for why in electrodynamics we also would expect something like this. And the argument goes as follows. So let's imagine we have massive electrons with some charge, E, and with the ordinary sign of the charge. And then we create a bunch of electrons here and a bunch of positrons here. So we have all electrons with positrons with positive charge, electrons with negative charge. Right? Now, ordinarily, it would cost some energy of order m to produce all these electrons, m times n, right? The number of electrons we produce. And here the charge, so we put them all together, the repulsive charge will be proportional to n squared, okay, that we have here. He said, what happens if we make, if we change e squared to minus e squared, right? If we change that, then we're going to change this sign. So with the negative sign, the like charges will attract, and so we'll lower the energy by putting them all together. And we minimize the repulsion by putting them far apart, and so we can lower the energy of the vacuum, and we have some instability in the vacuum, right? So we can decrease the energy of the vacuum, and this should lead to, this is similar to what happens with this potential, where we have, for very large lambda, an instability, and that's the origin of the lack of convergence, right? And the fact it is an asymptotic series. You can say, well, why doesn't this hold for this setup that we have here, right? So now imagine the same problem but in large n QCD, okay? So we have, we create, so the idea is that we create a bunch of gluons, right? So we create gluons, but when we create them, the indices of the gluons here will be correlated to the indices of the gluons here, okay? That means that if we have a pair of gluons, so when we create gluons from the vacuum, the indices are correlated in this way. That means that we will not have a factor of large n due to the, so this is k and l, etc. since these indices are not the same, we don't have the factor of g squared n. We have only a factor of g squared. Okay, so that means that at leading order in planar diagrams, we cannot use the same argument. These particles do not repel each other. Okay, when we change the sign of g squared, they only repel at self-leading orders in 1 over n, but not at the leading planar order. Okay. So that's why the argument that it should be asymptotic does not work. And yeah, is it clear? Well, it is clear why the usual argument doesn't work. But the fact that the expansion is analytic, well, if you want a mathematical derivation, you just this derivation we discussed here is basically counting the number of Feynman diagrams of various topologies. And we found that due to the fact that already for the Gaussian case we had an eigenvalue distribution which was big, so small changes in G or the coupling and so on, which has changed that's in a small way and will lead to completely analytic behavior. So that's the more sort of very first principles mathematical derivation. And that translates into the statement that the number of diagrams does not grow factorially. I mean, it grows like some power of... yeah, it grows in a way that leads to a conversion series. And even in ordinary perturbation theory, the idea is that the divergences come from the growth in the number of diagrams. So what counts ordinary diagrams is this integral. So this integral counts the number of ordinary Feynman diagrams with no planarity or anything like this. Okay.
Well, it's getting late, so
Okay.
more questions during the break. And one.
Sure. I think if you had a situation like this where the eigenvalues, I mean, if the endpoints collide, then I think they would have got